Just saying. Just saying.
That's great.
That's a great
expression.
Saying just saying is a great expression.
Just saying.
I think you're really stupid. Just saying.
Oh, my mom hates when I say just saying.
You just insult someone and then say just saying afterward. Okay. Right. Twitter. Make really inflammatory comment. Just saying. Just saying. Okay, so we're gonna do 18 again. If you did 17, you would have found, I think, that when you compare how much force is pushing it down the ramp to how much friction force is provided, there's the downward force down the ramp does not exceed the static friction. So I believe, correct me if you think I'm wrong on that. I think that's the case. For 18 though, 18 is very interesting. So here's a scenario. You got a ramp. Okay. And this is 37 degrees. And it says that we put a 40 kilogram block on here, and then we gradually increase the angle of inclination. Angle of inclination is just a word for like that angle. How steep is the ramp? And then the block starts to slide when theta hits 37 degrees. Does everyone understand the question? Okay. Obviously, that's what would happen, right? If you put something on a ramp, here's a good demonstration. Here's a full wear. That's not. There you go. Oh, no, it's gonna bend. I need something more. Box of cereal, maybe. Here you go. Cheerios. Buy Cheerios, everyone. Sponsored. So if you raise it, okay, it stays in place, but eventually you hit an angle where it's not moving, not moving, not moving. Eventually you hit an angle where the downward force exceeds the friction. Okay, so let's just jump straight to the result of like how much force pushes this thing down the ramp. What's the formula we derived? Mg sine of theta. So this vector here, oh, this is my batteries right now. Mg sine of theta. So this vector, Mg sine of theta, so take a calculator, go 40 times 9.8 times sine of 37. Let's see what they say. 40 times 9.8 times the sine of 37 is about 235.9. 235.9 newtons. Okay. How much friction force would there be? Here's the idea. This is a critical moment, right? Where this number just barely exceeded this number, right? So for all intents and purposes, I can set them equal. That makes sense. Technically, this number is slightly larger than this number, but we're just going to set them equal. So this number would be mu times the normal force, and the normal force is mg cosine theta. We're okay with that? Okay, so let's calculate that. The friction force would be mu times, let's get a number there. So 40 times 9.8 times the cosine of 37 is 313.1 roughly. Is everyone okay with that? Okay. So now what I'm going to say is, well, let's set those equal to each other, right? So 235.9 is equal to mu times 313.1, and then solving for mu is pretty straightforward from there. I wanted to, did I not put this in there? It's crazy. I swear I did. What? Well, it was 18. Okay, I guess maybe 19 will clear. it up. I guess I didn't make it a separate problem. At one point, I tried to trim this down so it was fewer problems. Because it used to be more, but. So anyway, but what I guess what I was trying to point out here is, and we'll do this in the next problem, but wasn't this value all along, wasn't this one mg sine of theta? And wasn't this one mg cosine theta? See what I'm talking about? So I know there's numbers here, which might kind of muddy the waters a bit, but look what happens. Does this problem have anything to do with the mass? Does the mass really come into play?
No.
Not really. How about the value of g? There's only one you could have totally actually right now. You could be like, actually, there is a specific case where g, the value of g would matter. Does anyone know what that would be?
Gee, I don't know.
What?
If it's vertical.
Oh, if this was 90,
Yeah.
that would matter. Yeah, that would throw things off. Similarly, I was thinking if g was 0. So say you were in a 0G environment, whether you're in deep outer space or say you're on an orbiting space station, then you see how the block would never slide no matter what. There's no gravity. So that, mathematically speaking, if this is 0 and this is 0, the equation is balanced no matter what the values are, right? Because you just have 0 equals 0. So anyway, you don't have to worry about that. I was just throwing it out there. Anyway, so if you solve this, you have sine of theta over cosine of theta equals mu. Who knows what sine of theta divided by cosine of theta is?
You.
Tangent of theta. So this actually boils down to a really simple formula, which is that mu static would just be the tangent. And let's confirm that. So you got a decimal for your answer, right? You got, I don't know what that would be. But, okay, 0.75 roughly. What's the tangent of 37 degrees? It's about 0.75. So this is a very nice, elegant formula for the. Now, you need to clarify something here. A lot of times people will get confused and go, oh, so anytime there's a ramp, the static friction coefficient is just the tangent of the angle. No, that's not what this is saying. This is saying that if you tilt the ramp and you get an angle at which the block starts to slide, say we call that like the critical angle where it starts to move, that angle, the tangent of that angle will tell you the static friction coefficient. So for 19, I'm kind of showing you 19 here basically. So for 19, you're going to set up this equation in blue here. Now it is an inequality, technically on 19. So for 19, your inequality is, you guys tell me, what direction does Mr. Alligator point? If you've got a ramp and you want to say, here's theta. This 19 says, what's the inequality describing the condition necessary for the block to slide down the ramp? So do I want this vector to be bigger than this vector?
Yeah.
Yeah, so I need this vector to be greater than that vector. Because remember, this thing here is sort of think of this as the capacity, the friction capacity. How much friction can this ramp provide for a given angle? And yes, we need the down the ramp force to be bigger. So divide the cosine underneath. This making sense? So hopefully this makes intuitive sense. We need, in order for the block to slide down the ramp, we need the friction coefficient to be smaller than a certain number, right? So I don't know, maybe you might have to think about that a little bit for it to click in your head, but okay. Let's do 20. This is the last thing we'll do today. We'll do number 20 together. Oh yeah, we got it. Doing good. It's not ready yet. I tried on Sunday. It needs another like foot before you're, unless you want to. Huh?
Sit close on something.
What?
My Chick-fil-A.
Good
You're
song,
my
Mr.
Chick-fil-A.
I don't know the song.
Oh my gosh.
How's it
Stephen
go?
Hawking's, isn't it?
What song?
No, it's Kanye West.
There's some.
Oh yeah, from that short album he released. Yeah, I do know that song. Close on Sunday, you're my Chick-fil-A. Something something. Yeah. Oh yeah. Okay. So number 20 looks like this. Mr. Trenton, what are you doing? Okay. You got a 30-degree incline. The block's 10 kilograms. But as we've seen, we could kind of ignore that, but let's just keep it in there. Okay, so number 20 is kind of an involved question because the first thing you have to do is show that it's going to slide down the ramp. So this vector is going to be mg, I'll just get a number. When you do mg sine of theta, what's going to come out here? 98 times the sine of 30,
49.
which is 49 newtons. Okay, the normal force is mg cosine of theta, which would be, this number's come up enough at this point. I think I remember it. Oops. Yeah, 84.9. Is that what you guys got?
Yeah.
So about 80. You all cool with that?
Wait, why would it? Wouldn't it be the force of friction?
Well, then I'm going to go up here and say the friction force. So first I have to say the static friction could be anything up to the static coefficient, right, times the normal force. So I'd say the static friction could be anything up to this times 0.4. So if I take my 84.9 times 0.4, I get about 34.0 roughly. Is everyone okay with that? Okay, so is it going to slide? Yeah. So it's going to slide. So then you go, well, I guess this isn't really happening then, is it? What's my new calculation? Kinetic coefficient times the normal force. So now my friction force is 0.2 times the 84.9. Is this making sense to everyone? So my friction force is about 17. Pretty close. I'm getting 16.98. So pretty close to 17. So we're sure there's no questions on that? So what's my net force then? Or what I should say is I write F net equals MA. What's my net force according to this diagram? Yes, very good. It's going to be 49 minus that 17. We're okay with that? The mass was 10, and so we get 3.2 meters per second. Acceleration. So, quick clarification. Do you have to show this as part of your work?
Yes.
Yeah, because you have to establish for the reader that this has been considered, right? You have to show that, because what if mu sub s had been 0.8? What if it was somehow like a huge static coefficient and a small kinetic? it wouldn't move. So you have to show first that it's gonna move, and then show the new calculations of the friction to get the net force. Very productive. Yep.